If you've ever had to compare two versions of the same thing, I'm thinking, two drafts of a report or maybe two versions of code in Git, that feeling of relief when the differences just pop.
Oh, yeah. Green for additions, red for deletions. It's instant clarity.
Exactly. And that whole system, that magic, is powered by uh, this really fundamental tool in computer science,
Hmm.
the Unix diff command.
Okay, let's unpack this. The elegance of it, the core idea, is really about finding what's called the longest common subsequence, or LCS.
Which is really just a fancy way of saying it finds the absolute shortest path, the minimum number of edits to turn file A into file B.
Right, and for things like text and code, it's brilliant, it's so precise.
And that word precision is everything because
Yeah.
diff and LCS, they have this really rigid view of the world. A character either matches perfectly or it doesn't. There's no middle ground.
It demands perfection.
Total perfection.
Yeah.
But our deep dive today is all about what happens when you take that rigid, perfect concept and, well, you drag it kicking and screaming into the real messy world. Right. What happens when you try to use that logic on something that isn't discrete, something that's continuous and flowing, like an audio signal or an electrical waveform inside a microchip?
Yeah, and our sources really map out this journey from demanding a perfect match to engineering a way to accept what's called a functional match.
Because when you first try it, you immediately hit a wall. They call it the digital cliff.
The great term for it.
So let's use that audio example. You've got two recordings of the same conversation. To your ear, they sound identical, a 99.9% match.
Perceptually, yeah, they're the same thing.
But you run a standard byte-by-byte diff on them, and the computer reports a 0% match. It says they are 100% different. That's the cliff.
And the reason for it is it's just physics, and it's so simple. It's almost infuriating.
I know.
I mean, say you have a tiny, tiny delay, 1 millisecond. Maybe one mic was just a little farther away.
Which is nothing. You can't even perceive that.
Right. But that 1 millisecond phase shift means that every single sample point, and there are tens of thousands of them every second, is now misaligned.
You just don't line up anymore.
They don't line up. Point 1 misses point 1, point 2 misses point 2. The entire comparison just fails catastrophically.
And you brought up another point from the sources, which is about just the sheer inefficiency of it all. It's not just that it gives you the wrong answer, it's that it's a terrible way to even try.
Oh, absolutely. The computational density is just off the charts. You've got, 44,100 samples per second for standard audio. Trying to run a classic LCS on that, I mean, you could wait for hours just for it to come back and tell you, sorry, everything's different.
So it's functionally useless.
Completely useless. You can't waste that kind of time.
Okay, so if demanding perfection is a non-starter, what's the very first fix? We have to add some wiggle room, don't we?
Exactly. Before you get into any of the really complex stuff, the simplest first step is to just introduce a bit of tolerance. You move from that zero tolerance policy to what they call a point-to-point comparison with a tolerance window.
Okay, so what does that look like?
Instead of demanding that a point from waveform 1 lands on the exact same coordinate on waveform 2, you draw a little box around the reference point.
Like a target zone.
A target zone, yeah. And that box has two dimensions. You've got your time tolerance, your t-tol, which is the horizontal wiggle room for that 1 millisecond delay we talked about.
Okay.
And then you have your signal tolerance, SOSTOL, which is the vertical wiggle room for, say, a tiny 1% difference in volume.
So you're saying instead of having to hit a perfect bullseye, you just need to get it on the paper.
That's a perfect analogy, yeah. If the second signal passes anywhere through that little rectangle, it counts as a match. And that one simple change that rescues you from the digital cliff.
But I can see a problem with that already. What if one of my recordings was made on a device that was running just a tiny bit slow? Like 0.1% slow.
Temporal drift.
Right. Over a few minutes, that tiny difference is going to add up, and eventually the signal is just going to drift right outside that little tolerance box, even if the shapes are still identical.
And that is the exact Achilles heel of the simple tolerance window. It handles small shifts, but not cumulative drift. And this is where it gets really interesting.
Okay.
To solve that drift, you need to go beyond a rigid box. You need an elastic ruler. And that concept is called dynamic time warping, or DTW.
DTW. I mean, it sounds a little bit like cheating, to be honest. If you can just stretch and squeeze the timeline however you want, couldn't you make two totally different signals look like they match?
That's a really critical question. And the goal of DTW isn't to force a match where there isn't one. The goal is to find the path of least resistance.
Hmm.
It non-linearly stretches and compresses time just enough to get the best possible alignment.
How does it know what the best alignment is?
It uses something called a cost matrix. It basically calculates the total amount of effort it takes to line up the signals. If they were already perfect, the path through that matrix would be a straight diagonal line.
A one-to-one mapping.
Exactly. But the moment the path has to deviate from that diagonal, when it has to stretch one part or shrink another, that deviation is the time warp. It's the correction it had to make. And conceptually, this is kind of like what voice assistants like Siri do to understand you, whether you talk fast or slow.
That sounds incredibly computationally intensive. I mean, if the original 44.1 kilohertz data was too dense for a simple comparison, surely doing this complex time warping on that same data is just impossible.
It would be, yes,
Yeah.
absolutely. Which is why the sophistication of the algorithm has to be matched by a really smart workflow. You have to pre-process the data. That's non-negotiable.
So what does that pre-processing look like?
Well, the first step is just brutal downsampling. We might take that 44.1 kilohertz audio and just drop it down to, say, 2 kilohertz. You're cutting the load by a factor of 20 or more. You're focusing on the macro structure, not every tiny detail. Then you convert to mono, and this is crucial, you perform amplitude normalization.
Why is normalization so important here?
Because you don't want a simple difference in volume to hide a real structural problem. Let's say one recording is just 10% louder. If you normalize both to the same peak volume, you can then focus purely on comparing the shape of the signals.
Ah, I see. So you're taking volume out of the equation.
Exactly. The comparison becomes about structure, not loudness.
Okay, so once you've done all that downsampling, normalizing, and then the time warping, what do you actually get? How do you find the real error among all the acceptable drift you just corrected for?
This is the really elegant part. DTW gives you a perfectly aligned version of your target signal. Let's call it B prime. Then you do a very simple calculation, the absolute difference between your reference A and this new aligned signal B prime.
So just A minus B prime.
Right. And the graph of that difference is called the residual map. If DTW fixed everything, all the drift, all the timing issues, that map should be basically flat, near zero.
But if there's a real glitch,
If there's a real glitch, a pop, a click, a dropout that time warping can't fix because it's a structural flaw, you see a sudden, sharp spike in that residual map. And there it is. You've successfully separated the acceptable timing difference from the unacceptable structural error.
the power of that is obvious for audio, but now we have to make a jump. We're moving from finding a pop in a music track to validating mixed signal memory chips, citing work from semiconductor design, like at Intel,
And the stakes just go through the roof.
exponentially higher.
Yeah.
The sources point out this incredible bottleneck where manual validation of hundreds of these waveforms was eating up to 70% of the entire design loading time.
70%. It's a staggering number. Just think of the engineering hours wasted, all because the tools were just flagging everything. They couldn't tell noise from a real error.
Which leads to the core philosophy that drove the entire industrial solution. And it's a quote I think we have to just keep in our heads. We need to compare for functional match, not graphical match.
That is everything. Because the old tools were obsessed with graphical identity. Do the squiggly lines look the same? But in a complex circuit, those lines can look very different and still be functionally perfect.
Right. And you broke down three main categories of these false alarms that were just plaguing the engineers.
Yeah, the first two are all about timing. You know, you get these tiny minor time offsets because of how gates are loaded in the circuit. Or sometimes the control unit will intentionally insert what's called a no-op instruction.
A do-nothing cycle.
A do-nothing cycle, exactly. It's completely benign, but it shifts the entire rest of the waveform by a few nanoseconds. And a rigid comparison tool just freaks out and flags thousands of errors.
And the third one is the big one, the environmental factor, the conditions the chip is running under.
The PVT corners, that's process, voltage, and temperature. You're simulating the chip under worst-case scenarios, high voltage and high heat, or low voltage and extreme cold.
And the chip is doing the same job functionally.
The exact same job. It's storing a bit of data. But the actual shape of the electrical signal, the waveform, will look different. The pulses might be wider, the voltages might droop a bit. Graphically, they are not the same, but functionally, they are 100% correct.
So with engineers drowning in these false alarms, wasting 70% of their time, they needed a purpose-built solution. And that solution was called WCOMP.
Right. WCUMP is this industrial toolkit built with two really intelligent strategies to get past this functional ambiguity.
Okay, so let's start with strategy one. How does it deal with all those timing shifts and no-ops?
This is the time shift comparison. And unlike DTW, which just kind of brute forces the stretching, WCOMP is smarter. It anchors its comparison to the actual functional states of the circuit. It uses the digital control signals to know what the chip is supposed to be doing.
So it's not looking at the clock, it's looking at the job description. Idle, reading data, writing data.
Precisely. First, it just confirms the sequence of states is correct. Idle, then read, then write. If that's good, then it aligns the analog waveforms, but it does it zone by zone inside each of those states.
So it basically resyncs the comparison at every functional step.
Exactly. And by doing that, it just naturally absorbs all those little clock shifts and no-op insertions. It filters out a huge category of false alarms right from the start.
Okay, so that handles the timing flexibility. But what about strategy two? How does it handle those PDT corners, where the signals just look different, but are still functionally correct?
That's the pattern comparison. And the goal here is to confirm that even though the signals have this environmental accent, they're still saying the same thing. And the tool they chose for this is a classic from signal processing called the Wiener filter.
A Wiener filter. So how does that act as a transformation engine?
Think of it like a mathematical translator. It looks at the golden reference waveform and the target waveform from, say, the high temperature simulation, and it calculates the optimal transformation needed to make the reference look like the target.
So it learns the dialect of the high temperature environment.
It learns the dialect. That's a great way to put it. It figures out the predictable voltage drops and pulse changes caused by that PVT corner. And once it has that transformation map, it can basically use it to normalize the signal, stripping that accent away.
Now, the sources make a really big deal about why they chose this classic deterministic filter instead of something modern like machine learning. That seems kind of counterintuitive.
It does, but it's the ultimate lesson in validation safety. When you're validating a chip that's going into millions of products, robustness is everything. A machine learning model, as powerful as it is, has a non-zero risk of a false positive.
Meaning it could see a bad chip and mistakenly classify it as good.
And that's the one thing you absolutely cannot allow to happen. So the designers chose a deterministic tool like the Wiener filter. They were willing to accept maybe a few more false negatives, where a good chip gets flagged for a quick manual check in exchange for near total certainty that a bad chip would never ever slip through.
That certainty is priceless.
It has to be.
So after the Wiener filter normalizes the shapes and takes out all the environmental effects, what's the last step?
You go right back to basics. Once the signals are aligned in time and normalized for the environment, you just run a final, simple point-to-point comparison. Any significant difference that's left over, that is your true structural error, a real glitch that has nothing to do with timing or temperature. It's the error that remains after all the acceptable differences have been intelligently stripped away.
So what does this all mean then? We've traced this idea of difference from its DNA. This fundamental logic used in Git to compare code.
Yeah.
It evolves into dynamic time warping to check audio quality, and then evolves again into a toolkit like WCOMP to make sure our microchips don't fail.
It's an incredible progression.
And the universal lesson here, whether you're talking about text or sound or silicon, seems so clear. Alignment must come before analysis. You cannot find a meaningful difference between two signals until you first account for all the expected acceptable ones.
You have to filter out the noise first.
You have to filter out the noise, the drift, the environmental effects. You have to synchronize the clocks before the analysis actually means anything.
And this whole journey really forced computer science to make a huge leap from just verifying graphical identity to truly validating functional integrity. Our algorithms had to get smart enough to know when something is working right, even if it doesn't look right.
Which leads to a final thought.
Yeah. I mean, think about how much we rely on this kind of validation today. Self-driving cars, analyzing LiDAR data, medical sensors, monitoring heart rhythms. How many critical life or death decisions now depend on algorithms that, just like WCOMP, have been specifically hardened to look past the false alarms and find the true underlying function? The modern world really does run on the power of that elastic ruler.